So this SpaceX rocket was fueling, then this happens. Boom! 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, bring the thunder, 10,000. Speed of sound is about 300 meters per second, so it travels about a kilometer every 3 seconds. 10 seconds, about 3 kilometers, 2 miles away, give or take. And that rocket cost about $60 million. And the satellite, which you can see here falling to ground sometime after the explosion, cost about $200 million. So that's about $250 million that just went up in flames there. So why did it actually explode? Let's start with the obvious. Most rockets explode from the business end. That's where the engines are, because once they're lit, what you've got is the fuel and the oxidizer coming into contact, and that releases a crazy amount of energy. And if that goes wrong, that can easily destroy the rocket. Actually, let me step back a bit further. What a rocket does is essentially mix a fuel and an oxidizer, which is usually oxygen, and it burns and gets hot and it expands. And it's that expanding gas which pushes the rocket forwards. The combustion process is actually very similar to what happens in your car. Apart from there, you have a fuel-air mixture, a much more dilute version. And it's those burning hot gases expanding which powers your engine. Now in your car, of course, you just get the oxygen to run the engine from the air. But you can't do that with a rocket because you just can't get enough oxygen into your engines. So you have to carry it, your own concentrated oxygen supply, which usually comes in the form of liquid oxygen. And ballpark numbers, a cubic meter of air contains about the same oxygen as 200 milliliters of liquid oxygen, so you can carry an awful lot of oxygen in liquid form. Now the problem there, of course, is that liquid oxygen is bloody cold, not far off the temperatures at which nitrogen liquefies. The practical upshot being is that you really can't have a greatly pressurized main tank for the oxygen of the rocket because it would just weigh too much, and your rocket needs to be light. So you have liquid oxygen in essentially an unpressurized tank. There is a slight overpressure in there, but it's not far off what you could blow with your lungs. Now, take pure oxygen gas on its own, and it's not too bad. But mix it with anything that will burn, say for instance like chicken flesh or cloth, and just give it an ignition source and it will burn like crazy. And so what I'm going to do first is I'm just going to light this, then I'm going to put it out, and then I'm going to dunk it into the oxygen atmosphere just to see what happens. So you'll see when I set it on fire here that it's just a sort of regular cloth, so it burns okay, yeah? I blow it out, and then when I put it into the oxygen atmosphere, the whole thing burns up in seconds, and just like that, it's all gone. So that's what your clothes would burn like in a pure oxygen atmosphere. Now what I'm going to do is I'm going to try the same thing again, but with something that would sort of equate to human skin. And what I'm going to use as a first proxy is chicken skin. Okay, so it's more or less the same deal. I've just got a piece of chicken on the end of a piece of wire. So what I'm going to do is I'm going to emulate what my burning clothes would look like from just I'm going to put a burning splint in there just under the chicken for just 1 or 2 seconds, okay? So we'll see what happens. So I'm going to blow that out, and here we go. So as you can see, people would burn really quite amazingly well, and the oxygen's mostly gone at that point. So as you can see, it's a very good thing that our atmosphere is only 20% oxygen, because if it was 100% oxygen, the smoking wouldn't just be bad for your health, it would be suicidal. And liquid oxygen is a brutally powerful oxidizing agent.
And this is the cheese puffs. Let me get the oxygen in there. Go ahead and hit them. Hold it there for a second. Okay, pull back.
Oh, wow.
Okay, see, that's why I brought the fire extinguisher as well.
Sure.
Similarly with petrol, gas, the stuff that runs your car, on its own, it's not too bad. But in air, a dilute oxygen atmosphere, it's a horrific fire hazard. Now, it's no coincidence that mixing liquid oxygen and gas, kerosene, gives you rocket fuel. And it's an incredibly energy-dense system. Kerosene and liquid oxygen was what powered the first stage of the Saturn V, and it's also what powers the SpaceX Falcon 9 rocket. However, in a rocket, it's just stored in two big tanks. There is no immediate fire hazard until you mix those two together, which is usually done in the rocket motor. That being said, once fueling has happened, the rocket is essentially a giant potential bomb sitting on the launch pad, which is why fueling is typically the last thing you do before launch. And of course, you evacuate the pad while you're doing it because it's so dangerous. Fueled rockets are just a massive hazard. Indeed, a fully fueled Saturn V contained an equivalent amount of energy to all of the bombs the Allies would typically use to destroy a city in World War II. Now, fueling a big-ass rocket takes a lot of time. So, for instance, to fuel the space shuttle, you had to pump about 700 tons of fuel into that external tank, and that took hours. I mean, that's the weight of about 35 big-ass tanker trucks that had to be emptied into this rocket. And if you watch fueling of a rocket in time-lapse, you can actually see where the liquid oxygen level is climbing and chilling the rocket, causing water condensation on the outside of the rocket. Okay, so the rocket on the pad is basically a giant bomb, and clearly, while fueling, it goes boom. But how could it actually go boom? You see, all you've got at the moment is two giant tanks, one of kerosene and one of liquid oxygen. Well, clearly, the propellants must have mixed to give this explosion. And when kerosene and oxygen are mixed, they give this really red, sooty flame, which is quite different from the clear flame that you get from burning hydrogen and oxygen. That's basically the difference between the exhaust of the shuttle and the Saturn V. Now, like I was saying earlier, all a rocket is pushing an oxidant and a fuel into a combustion chamber. Now there are two key and non-trivial problems with that. The first is, how do you stop the combustion chamber from melting? Because the flame temperature is typically higher than any metal you can make it from. And the second problem is, you've got a very high pressure in that combustion chamber. So how do you actually keep pumping liquid into it? Now, the melting problem is typically overcome by pumping the cryogenic fuels through tubes in the engine bell, thereby using your fuel to actually cool the rocket motor. And the pumping problem is basically what makes rocket science rocket science. It's a big-ass turbo pump that requires vast amounts of energy to run. I mean, it has to pump all of that fuel that took a couple of hours to pump into the launch vehicle into the engine bell at high pressure, something that is typically running at liquid oxygen type temperatures, in a couple of minutes. Typically 2 to 3 minutes is the burn time of most rockets. Basically, it's the engine's job to release all of this energy in a controlled fashion in a couple of minutes. And that's what makes rockets an engineering nightmare. The extreme conditions under which these engines run means that if anything goes wrong with those pumps, this sort of thing can quite easily happen.
Then a failure occurred involving one engine. And shortly thereafter, another engine also lost power. It was therefore necessary for the range safety officer to destroy the missile by remote control.
And the rest is just structural failure of the rocket, which is basically two giant fuel tanks. So back to our SpaceX explosion. Well, clearly the explosion doesn't come from the business end. Well, actually not entirely. There is a second stage on this rocket, and now it looks like that's where the explosion comes from. So a little chemistry. You actually need quite a lot of oxygen to burn kerosene, which is why you need a bigger tank for the liquid oxygen than for the fuel. So ballpark numbers. There's a factor of about 1,000 expansion from turning liquid oxygen into gas, which is basically true for most gases. And when you burn that with the fuel, you get a further factor of 10 expansion because of the heat. So basically a litre of rocket fuel gives you a factor of about 10,000 expansion in gas, ballpark numbers. Well, we know the size of the rocket. It's about 3.5 meters in diameter. So we know that the initial fireball size is about 20 meters, about 20 yards in diameter. Well, if you know the diameter, then you can calculate the volume. So about 3,000 cubic meters is the volume, and that fireball was after a factor of about 10,000 in expansion. So that would have required about a third of a cubic meter of liquid fuels to be mixed for this explosion. A cubic meter of these sorts of liquids weighs about a ton. So it's about a third of a ton explosion here. That's 300 kilos, about the weight of 3 people of rocket fuel. Now that might sound like a lot, but it's actually not that much when you consider a rocket like this weighs about 500 tons, 400 tons of which is propellant. Then of that, generously, maybe 1% of the fuel mixing caused this initial explosion. However, those propellants shouldn't be able to mix until they get into the combustion chamber. So what sort of things can go wrong that would allow a problem like this to occur? Well, typically with these things, you're looking for a single failure. And the most obvious place where you can get a single failure that'll mix the two fuels is where the two fuels are in close proximity, separated by a single wall. Now, two obvious thoughts spring to mind. The first is that rocket designs like this, the oxygen pipes typically have to go through the kerosene tank at some point, and those pipes typically have to be straight because of the high liquid oxygen flow rates needed for big rockets. And the Falcon 9 is a big rocket. So basically, those pipes typically go straight through the middle of the kerosene tank. And that kerosene will quite happily freeze at liquid oxygen type temperatures. And to aggravate this, the Falcon 9 chill their kerosene as a trick to make it more dense, which means they don't take up so much space, so your tanks don't need to be as big. It's a sort of weight-saving thing for the rocket. Now, I don't know how the Falcon 9 deals with the problems of the kerosene freezing, let alone on the second stage. But it's an obvious point of failure in that a leak here would allow you to get the kerosene and the oxygen in direct contact. So, for instance, if you had the kerosene freezing around the oxidant lines, they could have stressed and cracked the fuel tank. Alternatively, a failure in the oxygen tank or just a leak in the liquid oxygen could cause similar stressing and failure of the fuel tank if that liquid oxygen ends up on top of the fuel tank. And this is one of the things that bugs me about people who gush over Elon Musk. All the problems I've talked about here have been explored in depth and solved long before he or I were born. But people still get ecstatic over this. Yeah, this is impressive, but let's keep this contribution in perspective. I mean, recovering a rocket actually has a lot of technical drawbacks. I mean, the first one being is with a rocket, you typically get your best bang for the buck out of the last bit of rocket fuel. That's rockets are typically 90% by weight fuel. A rocket engine produces effectively constant thrust. So typically when you light up your rocket, it's only just powerful enough to lift itself off the ground. It's got a very low acceleration
Ignition
when you start.
6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
And then as you burn off progressively more of the fuel, the rocket gets lighter. And so as you're producing constant thrust, you get more and more acceleration as the rocket gets lighter. Indeed, with the Saturn V missions, they had to shut down some of the engines early, because otherwise the acceleration would have killed the crew. Well, actually, maybe not that bad, but they were getting up to 3G, which means a 100-kilo person would weigh about 3 times that much. And it puts lots more stress on the rocket and so forth. The bottom line is, when you burn your last bit of fuel, you get a lot more speed out of it than you did for your first bit of fuel. Now, this is, of course, an advantage that you lose with the Falcon, because you have to save enough fuel in your rocket to actually decelerate it and stop it suffering heating when it re-enters the atmosphere, and enough fuel to land it. Now, that's not entirely a fierce burden in that when the rocket lands, it only weighs 10% of what it did when it took off. I mean, where it lands, it's basically an empty rocket, but it's still a disadvantage. And in many ways, I'm surprised they didn't go the sort of way that NASA did with Mars, that you start off with a couple of parachutes and then only light the rockets for the last little bit of the journey. Now, as a payoff for this, you do recover your rocket engines, which is where it again gets tricky. I mean, this is not the end of the story. Even if you can recover the engines, which isn't a new thing either. The shuttle was doing this for over 30 years. Now, you'll recall earlier that I said that the real problem with these things, these rocket engines, was the fuel pump. And I'm not so sure about the economics of this. Sure, it sounded like a great idea, but then again, it sounded like a great idea with the space shuttle. And it still ended up being one of the most expensive launch vehicles on the market. And for those who are like, rah, 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 Musk can do anything. No. While they've recovered some of the launch vehicles, as of 3/4 of the way through 2016, they've never reused any of them. Plus, I can't remember the last time I saw a rocket blow up while fueling, because those problems were solved a long time ago. I mean, Wiki actually informs me that the last time that NASA had a fueling explosion was some 40 years ago.
The possibility that trouble may develop with the Atlas or the Redstone during the countdown or during the takeoff is looked squarely in the eye by the astronauts and the engineers behind Project Mercury.
I mean, for many of the free enterprise will make space cheap and accessible, don't seem to have realized that sure, there may be some savings to be had by the free market. But organizations like NASA basically wrote the rulebook on this sort of stuff. They would never have allowed a design like this off the drawing board, where merely making a single mistake in flipping one switch could lead to a catastrophic failure and loss of the vehicle.
Scaled composites did not emphasize human factors in the design, operational procedures, simulator training, or hazard analysis for Spaceship Two. Although Spaceship Two program personnel said they were aware that unlocking the feather during transonic flight would be catastrophic, there was no warning, caution, or limitation in the Spaceship Two pilot operating handbook or on the PFO4 test card that specified this risk. In addition, human factors was not fully considered in Spaceship Two training, as the simulator did not replicate the vibration and loads, nor did pilots train wearing the same flight gear that they were expected to wear during actual flights in the vehicle. Scaled missed opportunities to identify design and/or operational factors that could have mitigated the catastrophic consequences of this single human error. Although Scaled engineers reference some military standards and FAA circulars, because commercial spaceflight is an emerging industry, no human factors guidance currently exists specifically for commercial space operators.
So yeah, this is impressive, but it should be kept in perspective as an incremental development in rocket design. And just like with other concepts of reusable spacecraft, it remains to be seen if this is going to be a profitable one.